Alright, so in this video we're going to have a look at results for sums of more complex series. So more complex sums, and it's exactly the same process, but we're going to look at this kind of specific example. So remember, a lot of the stuff we're doing in this section is quite formal. So the first thing we're going to write is proof by the principle of mathematical induction. However, you're going to write the full thing out. I am not. So apart from the end, I will again. So proof by principle of mathematical induction. So the first thing we want to do, one, like always, is prove for the first term, so n equals 1. So if n equals 1, what we get is, I'm going to label this my left-hand side and my right-hand side. If my left-hand side equals, so for n equals 1, it's that first term, which is 1 times by 2, which equals 2. Okay, split my page in half. Now for the right-hand side, it's going to be putting the ones in there. So 1 times 1 plus 1 times by 1 plus 2 divided by 3. Okay, now we do the brackets first due to bed mass, so it becomes 1 times 1 plus 1 is 2, 1 plus 2 is 3, divided by 3. Okay, if we do the top row, 1 times 2 times 3 is 6, 6 divided by 3, 6 divided by 3 is 2. So therefore, P of 1 is true. Okay, and they usually come out pretty nicely like that. The only other thing is maybe I could have written P of n equals this thing, but yeah, we hopefully could recognize that as well. So we've done part number 1, now on to part number 2. So we're going to start by drawing that little 2 again. So part number 2, if P of k is true, then we'll write it out. So it's going to be 1 times 2 plus 2 times 3 plus 3 times 4 plus plus n times by n plus 1. Except what I want to do is I want to use my k's this time because we're calling it P of k. So we call it k. Lots of k plus 1, and has to equal the other side. Has to equal k, lots of k plus 1, k plus 2, divided by 3. Okay, so that's what we do. We set up P of k. So that's going to be a P of k, and it's going to come into play later. So now, so again, these all flow the same, even though we're looking at very different. So this flows the same as the previous video. It will flow the same as the next. Just got to work out how to do the maths in between. Now, for P of k plus 1, so the next domino in the line, we get 1 times 2 plus 2 times 3 plus 3 times 4 plus blah 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 plus. So the next one in line is going to still have this term plus k, lots of k plus 1, plus it's going to have an extra term, so a k plus 1th term. So this first part, change to k plus 1. So change that one, times by k plus 1 plus another 1. Okay, so maybe that's not very clear. So I've changed this second k plus 1 into a k plus 1 plus 1. All right, that's a k plus 1th term, and it has to equal this side here with k plus 1s as well. So k plus 1 times k plus 1 plus 1 times k plus 1 plus 2. And if you're sitting there thinking, couldn't I have just written k plus 2 here? like this? Yeah, you can. And you could have written k plus 3 here. It's the same. All right, same as over here. You could have just written plus 2. All right, if you recognize that straight away. So what we've got is now k plus 1 is this term. So again, the kind of the tricky thing with this stuff is just recognizing that this here, it's good that I have this color, this square here is the same as this one. Okay, so those two are the same, but we said that this original one was equal to this. So I can substitute this into there because they're equal. We've proven that they're equal, so same, we can put them in. And that's exactly what I'm going to do. So I'm going to put that in there, so I get k, lots of k plus 1, k plus 2 over 3, plus I get this extra term, plus k plus 1, times k plus 2. All right, so that's our new form. What we can do though is we can simplify it, and the way we do that is by putting them on the same denominator, making them have the same denominator. So this one's being divided by 3. So if I want to divide this by 3, I can do that, as long as I multiply the top by 3 as well. So 3 divided by 3 is 1, so I'm not changing anything, but I'm allowing these to be added, which I'll do now. So I can just straight up add them. They're both over 3, so I can make it a big denominator of 3. And I've got the first part, k lots of k plus 1, k plus 2. And I had to add that extra 3 to make it work, so I've got 3 lots of k plus 1, k plus 2. So when we get questions like this, often they're written to come out nicely, so we can realize on this left-hand side of the equation, we've got k plus 1, and we have it here as well. So on either side of this addition, when we see that, we know we can factorize it out. So we can say, all right, because k plus 1 is on both, k plus 1, oops, let's just imagine that's a 1, is on both, we can factorize that out and see what we're left with. Okay, so we're left with k times by k plus 2 plus 3 lots of k plus 2, because I've taken out those two underlying green things, all divided by 3. Now again, if you're good at factorizing, you might realize that there's a k plus 2 and a k plus 2 here. So we can factorize that out as well. So we get k plus 1. Let's take that k plus 2 out the front, k plus 2. What are we left with in the brackets? We're left with k on this side and nothing else, plus 3 on this side and nothing else. That's all divided by 3. All right, now the good thing about this is we can see we got k plus 1, k plus 2, k plus 3. If we went back to when we substituted in k plus 1, here, we saw we got k plus 1, k plus 2, k plus 3, all over 3. So this one is exactly matching that. And that's the whole point of this induction. So what we say is, therefore, p of k plus 1 is also true. So you'll notice that these statements here are the same, and in between them is like a sandwich of maths that changes each question. So again, we've got to finish off with our formal writing. So I'll just clear some room. So since p of 1 is true, so since p of 1 is true and p of k plus 1 is true for all p of k, actually I'm going to rewrite that. Since p of k is true whenever p of k is true, that means our p of n is true for all All right, sneaky way of writing for all is this upside down A. So for all, if you wanted to, for all of our n's belonging to the real positive integers, and we've done it. And we just have to write that is due to the principle of mathematical induction. Okay, so hopefully you saw in this one that, again, it was quite different, but sandwiched between the maths that's different, everything in between that is the same. So we're going through the same formula. We're always starting with the principle of mathematical induction, finishing with it, and trying to prove for P of 1, for P of K plus 1. So those things are all the same, although the maths changes in between. Okay, thank you.